Hi, I'm Ben-Yaakov. This presentation is entitled Current Sharing of Parallel Connected Power Supplies by the droop method. The presentation is in collaboration with Evgeny Smidotsky. There are a number of reasons why we would like to connect power supplies in parallel. One of them is redundancy. That is, we would like to have the load being supplied even if one of the power supply fails, so that we have current going to the load in the case of failure of one power supply or more. Then there is another reason, and that is if the power supply itself is insufficient to provide all the current to the load, then we would like to have more power supplies connected in parallel so as to supply the required power level. A third reason is that if we would like to increase the reliability of the system, we can run the power supplies at a lower power level. The temperature inside will be lower and the reliability of the system will be higher. So there are a number of reasons for connecting power supplies in parallel. Now, if you just connect two power supplies in parallel, having a low output impedance or resistance, because this is a voltage source, and since the output voltage of a power supply is not an exact value, there is a spread here, and also it's temperature dependent, then if you connect two power supplies, chances are there's going to be a very heavy circulating current because one of the power supplies will have a higher voltage, and this will induce a short circuit as a matter of fact between the power supplies. Now you can block this circulating current by having diodes. Now diodes have a voltage drop across them, so at high current the dissipation will be high. So you can use like an active ideal diode, meaning that you have a power MOSFET in parallel to the diode, such that when the diode is supposed to conduct, you turn on the transistor, and so the voltage drop is just due to RDS on, and of course if the power transistor is of high level, then RDS on will be low. So this will be a way to lower the dissipation, but still we do have the problem that if one of the power supply has a higher voltage, it will take over and all of the current will be passing through it because the voltage here at the output will be higher than the voltage of this power supply, so this one will not provide any current. So this is not good, of course. To remedy this, we can add a droop resistor, and this is the subject matter of this presentation. Now the objective here is to make the current as close as possible, that is to have current sharing between these two power supplies. Okay, so this is the objective of adding a droop resistor or having a behavior with the droop of the power supply. So here is a graphical illustration of the situation that we have. This is the nominal value, say, of one power supply, and then this other power supply has a, say, a lower voltage, okay? So there is this delta V between these two power supplies. Now, if we have a droop, then as the current builds up, the voltage of the power supply will drop, and this will be the drop in the voltage of the output across the load. Now, the current deviation between the two power supply is this value here between these 2 points. For this particular voltage level, this is one power supply, the other one, and here is the deviation, and I'm assuming that this is like the nominal value, the total output current divided by N. In this case we are talking about 2 units, of course there could be many more units. Now if the droop resistance is larger, then we have a larger drop, but the deviation of the current is smaller. So there is a relationship between the resistance here and this delta I, so we can actually adjust the delta I by selecting the proper droop resistor. So we can see that the larger the droop resistance, the smaller will be delta I, but the drop in the voltage will be larger. So the approach for designing a system like this can be based on 3 starting points. Either we want a certain delta V, that is, we want a maximum of change, or a certain delta I, or in some cases we like to make sure that the current of each power supply is lower than the I maximum. That is, we don't care if they are equal, but we don't want the current of each one of them to be larger than allowed. Now, in this presentation, I'm assuming that the starting point is this delta V. That is, that we have a requirement for a certain delta V, and the question is what should be R, and then what will be the resulting delta I in this. Now, based on this simple model, and using some geometrical relationship between these deltas and I's, we can develop a set of equations here. I'm not going into the fine details, but let me start first of all with the definitions that we have here. Now, V% is the drop in the voltage referred to the nominal voltage in percent. I% is delta I over the total current, and then reference percent is the actually error in the output voltage, or the deviation of the output voltage, which is primarily caused by the accuracy of the reference of the controller. So this is the deviation, the expected deviation in percent. And RL is defined as the nominal voltage times the nominal current. Now, again, the starting point is V%, and using this geometrical relationship, we can find that given this V% and given the deviation of the voltages, the output voltages of the original power supply, we can find that the I%, this is the delta I in percent, is this expression here. And then we can also find what should be the resistance for this required V% given RL. Okay, N is the number of units that we have. And this can be illustrated by this graph. What we have here is this V%, this is what we want. Delta I, or I%, is what we are going to get, and this depends on the error of the original error of the output of the power supply. This is the deviation, the reference accuracy, and in this particular case, I'm showing a case in which we ask for 7% maximum of deviation of the voltage, that drop, and given that the reference deviation or accuracy is 3%, we would expect a total of 40%, and assuming 4 units, I'm going to show an example of 4 units, then it will be 10% for each unit deviation from the expected value, from the value in which all of them are the same. So to test this, just to illustrate it, I've set up this LT-SPICE schematics. We have here voltage sources, we have these droop resistors, and I'm starting with 10 volt as the nominal value, and then just to have an extreme case, I've put all the other one, the 3 units, with an error of 3%. Okay, we have 3 units larger voltage and 1 unit nominal voltage. I'm assuming a output current of 20 amp. The nominal voltage is 10 amp, so RL is 0.5, here it is. And I'm assuming that I want a 7% deviation, or I agree to 7% deviation. Okay, this is this point here. And from the equation shown here, we can find what should be the resistance for this particular requirement of V% in RL, and it comes to be 140 milliohm, and here it is, this is 140 milliohm, these are these resistances. And here is what I'm getting. Now, this is the voltage. You see there is a drop to 9.55, which is a deviation of 0.45, so from 10 it's about 4.5%. And then you see the current, the nominal value should have been 5 amp, because we have 20 amp divided by 4. But you see that this one, this IR2 is close to the value, to the 5, but this one is farther away. And in fact, if I sort of summarize what has been resulted from the simulation, I see that I started with this. I actually got 4.5% for this particular case of 3 units larger voltage, etc. And then this should have given us a deviation of a current of 16%, total 65 divided by the 4, 16%. while in reality we have actually measured 9%. Okay, so you can see that these equations are not exact. They are just a starting point for a design. You can use them as a first iteration, and then you can improve on it. And one way to do it is to use a simulation. And for example, you can use a Monte Carlo statistics and then run a Monte Carlo simulation. This is in LT spice. You see this means that the nominal value is 10 and the deviation is this reference, which in this particular case it's 1%. And I'm running it 1,000 times, and I'll be looking at the current of this one, and of course I can look at the other voltages. This is just the calculated value here. So here it is. You see that for this particular case, 1%, 4 units, we have a deviation of the output voltage down to approximately 3.5%. Okay, this is much lower than that. And then the current of this branch that I'm looking at is nominal should have been 5, and I see here a deviation of about 1 or 2%. So this is a statistical result assuming a 1% deviation of the nominal output voltage of the power supplies. And this is just another look at the same thing. This is the run up to 1,000 cases, and here is the current. This is the current of power supply, and we can see actually the worst case. Again, 5 is the expected value, and it goes to a maximum of 7 and about 3, so plus minus 2 amp, and 2 amp from 20 amp, it's about 10%. Now, using a passive resistor for the droop resistance has its shortcomings, of course, especially the fact that you have power dissipation across this sense resistor. So if you have a high current, the dissipation will be very high. So there is a way to overcome this by implementing a active droop behavior to the power supply itself. Now the idea is the following. We are measuring the output current, and as a function of this output current, reducing the voltage by a feedback. So what I'm showing here is the original power supply control. This is the power supply. This is the reference of the power supply, the summing point, compensator, modulator, and power stage, and that's the output voltage. K is the voltage divider between the output and the reference. Usually the reference says 1 volt, and here I like to have 5 volts, so K will be 1/5. And then we have another to get a voltage, and this voltage now is subtracted from the reference. So as the current goes up, we are making sort of the effective reference smaller and smaller. So if I have a delta I here, the voltage change here will be this R prime times delta I. The reference is now V reference minus R prime delta I. And as it comes to the output, of course, because of the K, it will be 1 over K time larger. So this is the output. So therefore you can say that R prime over K is the effective droop resistance, okay? So this is the effective droop resistance, is the R prime divided by this K, this voltage divider between the output and the reference. There is another way which actually is better, because adding something to the reference is not very convenient. Many controllers on the market do not have access to the V reference. You can't get to it. On the other hand, we can inject or change the voltage at the sampling point of the feedback, and this is now will be by adding some voltage so that the system think as if the voltage is higher, so therefore the effective voltage will be lower. So by this we can have the same effect, and the coefficient will be the same, except that we are injecting now, adding a delta V to the sampling point. And here I'm doing some simulation to illustrate this active droop. So here are 2 units from analog devices, a demo circuit in LT-Spice that I'm using, and I've added here a voltage source of 0 for measuring the voltage. That's the classical way of measuring current. You can refer to the current of a voltage source, and if it's 0, it doesn't make any difference to the circuit, doesn't affect the circuit. This is an ideal diode. This is a parameter of this diode, so the forward voltage is small and the resistance is small. And I've also added a 10 milliohm in case you like to measure the voltage across it, just to have it in the circuit. So we have 2 units here, and the injection is done by actually sampling the current here and injecting some proportion of it to this point. However, I'm starting the simulation with no injection here. You see that this 0 times this current, 0 times this current. I'm only adding some DC to this point. Now this will cause, of course, a shift in the output voltages of these 2 power supplies. So I'm starting with the case in which I have no droop, but I have 2 power supplies, and one has a higher voltage. This is higher voltage because I'm adding voltage here, so the output here will be effectively lower. And here is what I'm getting. What I'm showing here is the current of the 2 branches, of the 2 outputs, and you see that this I1, this is this one here, is going up because I have a load which is changing with time. It's a ramp because I have here a current ramp changing with time from 0 to 15 amp, so it's going up. So we see that the current is coming out of the supply with the higher voltage, while this one does not provide any current. We can see that the current of the inductors here, this is the ripple of the inductor. This power supply is now operating while this one is actually blocked, does not feed any current. Now I'm adding this feedback. So I have here 0.1 micro times the current. So this is the current coming out times 10 to the minus 7, and I'm injecting it with a current source. Of course, you can have a voltage source with a large resistor, but just for the sake of demonstration, I've put here a current source. So I have the 2 injections, the same thing here, and here I'm also again adding this DC so as to make the 2 power supply different in terms of the output voltage, original output voltage. And here is what I'm getting, which is very nice. I see the current of one power supply, the current of the other power supply. This is the ramp. See now the step. There's a step here because I've added here a step current, a step load of 1 amp, a short one. And you see it here, and you see very nicely that the dynamics is pretty good, that both of them are reacting very nicely. And here we have the current going up. This is the difference in the current, and we see the drop in the voltage, total voltage. Of course, when you have the step, there is also a drop here in the voltage, and this is the slope, this is the droop, in fact, due to the fact that the internal resistance of the power supply now is higher due to the internal feedback from the current. Now let's do some sanity check here to see what we got and what we would expect, and if they are actually in agreement. So let's start first of all with this R prime. This is the relationship between the current and the injection. Now we have the current, we multiply it by the 10 to the minus of 7, and we are injecting it here. But the voltage here really depends on the impedance or the resistance, which is 100K in parallel for 562. So this is the parallel combination of the resistance. It should be kilo ohm, and this is the 10 to the third, and this is the 10 to the minus 7, the coefficient here. So the R prime, as we called it, is 8.5 million. Okay? Now the K of this circuit is 100 divided by 100 plus 562. Here it is. K is 0.15, and therefore the resistance that we are emulating is this R prime divided by K. R prime is 8.5, K is 0.15, so it is 57 milliohm expected to be. So we expect that the output impedance of this unit now is 57 milliohm. I'm talking about the voltage here. There is another 10 milliohm here if we are looking at the total output. So let's see what we are actually getting. So I'm looking at the output of one of the power supply. That is, I'm looking at the output here, okay? And at the current of it, this is the current, and this is the output. And of course, when there is a pulse, and in this case, I've made the pulse larger, so the drop will be more significant, so I can measure it. And this here, we can see it zoomed. So this is the load step, the 2.45 amp. And then this is the drop of the voltage, which is 136 millivolt. And therefore, the output impedance of this unit is this ratio here, which is 55 milliohm, while what we have estimated here from this calculation is 57. Simulated here 55, expected 57. This is very good. So let me now move to another issue, which is kind of very interesting. And this is looking at the current of the output of each of the power supplies. This is not the total current, this is the current of the unit itself. This is, I'm looking at the current here, not the current here, but the current here, and the current here. And what we see here is this region here, it looks something like oscillation. Now we don't have it here, and we don't have it here. So what is it? Well, it turns out that it is not oscillation. Okay, so let's try to understand what it is all about. To understand it, I am first of all referring to the interleaved buck configuration that has ripple cancellation. Now, if I have two inductors, two-phase buck converter, and then I connect them together into a capacitor, then I'd like to run them such that the ripple will have a shift of 180 degrees, so it'll be sort of opposite polarity. So therefore, the current here will sort of cancel out, and there'll be a minimum ripple on this capacitor. This is in this particular case. This is for 2 units, and the shift should be 180 degrees. Now, the case we are talking about is not this one, but this one. We have a power supply which has already a capacitor in it, and then we connect the output, okay? Connect the output. Now, if the ripple on the capacitor here and here will be the same, there will be no circulating ripple here. On the other hand, if the ripple on the capacitor will be different or lower or different from the ripple here, we're going to have a circulating current here. So in this particular case, we would like to have the two currents synchronized of the inductors such that the ripple here and the ripple here will be the same because the currents are about the same. So let's see what is really happening. So I'm first of all looking at this area here, okay, and this area here. And this is the current. You can barely see the ripple on it. And here is the inductor current. And you see that indeed they are in phase, and the ripple is about the same amplitude. So therefore the ripple of the capacitor is the same. And this is the reason why there is no ripple at the output. On the other hand, if we go to this region here, now at this point, this power supply is still in a discontinuous mode. So we can see it here. Here it is. This one is already in the CCM, continuous current mode. This one in discontinuous current mode. Now, obviously, the currents are not, the ripples are not the same, and there is also a shift because there is some pulse skipping here in this controller. And consequently, the voltages on the capacitor will not be the same, and there is now a ripple. So this is the reason for this ripple. Here it is. And here is the actual voltage across the capacitors. That is the voltage here and the voltage here. And the circulating current I'm talking about is this circulating current. So this is the case in which we have no ripple, and this is when the ripple, voltage ripple, on the capacitor is about the same, okay? And then the current ripple, or the circulating ripple, is very low. On the other hand, in the other region, when the current of the inductors are not the same, we have a different ripple, voltage ripple on the output capacitor. This is the output capacitor, and therefore we are going to have a ripple in the current. It's a circulating ripple between the two units. Very interesting. Now I'd like to wrap this presentation by showing another way to measure the current. Now there is another way which is sort of elegant, in that you add a RC circuit, RC, in parallel to the inductor. And the idea is the following. If the inductor has a resistance in it, and in fact this inductor has a 2 milliohm resistance, only it doesn't show up at the labels here, but if you click on it, you'll see there's a 2 milliohm, okay? Then if the time constant of this inductor and resistance is equal to the time constant of the R and C, one can show that the voltage across the capacitor is in fact the current through the inductor. It's a neat way to actually use the internal resistance of the inductor as a measure, as a sense resistor, you might say. So here I'm actually sampling this voltage. Then I've added 1 megohm to convert it to a current, because if I just have a voltage source here, it'll short it out. So I have a 1 megohm. And then since I've added a 1 megohm, I've sort of messed up the voltage divider, because now these two are in parallel. Original one was 100 kilo ohm. I didn't have to do anything with the current source. But now, since I have 1 megohm, I've changed this one to 110. So in parallel, they are again about 10 kilo. Okay? So instead of measuring the current here, I'm measuring the voltage across this capacitor of this network in parallel to the inductor. And here's what I'm getting. The behavior of the current, the output current, is about the same, okay, as we had it before. Here's the droop again, very similar. And here I'm actually showing the injected current. Now, if I'm just measuring the current and injecting it, it's a fairly smooth current. But if I'm looking at the voltage across the capacitor, it's actually emulating the current of the inductor, which has a ripple. So this, in fact, here is the ripple of the inductor. Now, the injection of this signal with the ripple in this particular case does not cause any big problem, because it's a very high frequency ripple. The switching frequency of this converter is 2 megahertz. Now, the bandwidth of the control is much, much lower than that. So therefore, it doesn't make difference. Actually, it's been filtered out, and what the controller is really seeing is an injection like this. So you can use this idea. Now, obviously, you need a differential amplifier to measure the voltage here, which is sort of floating, and then provide a signal which is referred to ground. But this, of course, you'll have to do also if you're measuring the current across a sense resistor. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.